answer this question that we have. So we're going to be using this table. The question we're answering, it says Townsend Realty purchased the Glenview Street property and received a 40% discount off the original price with an additional 20% off the discounted price. So it's been discounted twice. It had a 40% discount, and then off of that 40% discount, it had a 20% discount. So that matters because conventional wisdom would say that we could really just take it and multiply that by 1.6, and we would be able to get close to where we're at. But in this case, that's not it, because we took 40% off and then we took another 20% off of that. So which of the following best approximates the original price in dollars of the Glenview Street property? Okay, and if we go to our table, it shows the Glenview Street property. We purchased it for a total amount of $140,000, and this is after the discounts. So we're trying to find the original price. So what we're going to do is we're trying to find X, the original price. All right, so I'm just going to nominate X as the original. So from this, what did we have to do to X to reach 140,000? Well, first we discounted it by 40%, right? 40% as a decimal is just 0.4, and we subtract that from 1, we're left with 0.6. So we know that it's 0.6x because that is the original price, right? And all of this is going to be set equal to 140,000 once I get done. But off of that discounted price, we also had an additional 20% taken off, right? So 0.2 taken away, if we subtract that from 1, we get 0.8. Okay, and we set up a nice little equation here. The price we ended up paying, the original discount was 60%, right? Because they discounted it 40%, so we're paying 60%. Then our additional discount of 20% means that we're paying 80% of the already discounted price. So if we distribute this across, we'll end up with 0.48x is equal to 140,000. And then if we divide both sides by 0.48, plug it into my calculator. I'm not that good, and it's early in the morning. So 140,000 divided by 0.48. That leaves you a value of X as 291,666 and 0.66 repeating. Okay, so looking at our answer choices, which is closest, that would be answer choice B for $291,700. This one is just a little bit tough because we have to understand what the discount does, and then there's a sequence to them. So if we get a 40% discount, that means we're paying 60% of the original price. And then since we got a 20% discount off of that discounted price, we're paying 80% of that. That's why you set it up like that and then distribute. That's how you got 0.48. I like that marker, it writes good, but it's not very easy to erase. That's going to be a problem, I have a feeling. But other than that, it should be pretty good, hopefully. So, but on the bell work, correct answer is B. All right. So now let's go off to our 5-minute check over condensing and expanding. So remember, today we're going to be solving logarithmic equations. Condensing and expanding is the way that you do it. Okay. So first question, we want to express the natural log of 4/7 in terms of natural log of 2 and natural log of 7. So this one's fairly simple. So the natural log of 4/7 per the quotient property that we learned, that is equivalent to the natural log of 4 minus the natural log of 7. right? And we want to get it into terms of natural log of 2 and natural log of 7, as the answer says. So what can I do to 4 to manipulate it to get it into a base of 2? Well, 4 is 2 squared. That's the natural log of 2 squared minus the natural log of 7. Then we would use the power property of logarithms to bring our 2 out front. We're going to be left with 2 natural log of 2 minus the natural log of 7. Pretty simple question because they dictate what our answer has to be or what properties or how they want it expressed. So nothing too terrible there. Yeah, that's going to be a big problem. Maybe if I try an actual clean eraser, that'll help. Remember, as long as anything's equal, we can substitute it in. So that's the key to getting it into the terms of 2 and 7. Next one, express the natural log of 56 in terms of natural log of 2 and natural log of 7. So this one, once again, we have to manipulate 6 or 56 to get it into terms of 2 and 7. So one of our numbers is pretty solid, right? 56 is 8 times 7, and 8 is equivalent to 2 cubed. So what that would look like is we take the natural log of 56, and that's equivalent to the natural log of 2 cubed times 7, right? Then we use the power property to split those. The natural log of 2 cubed plus the natural log of 7, or the product property to split those. And then we would finish up using the power property, get 3 natural log of 2 plus the natural log of 7. Right there. All right. Okay, this one we're expanding. We're given log base 2 of x squared divided by the cube root of x plus 4. So again, we want to take a gander at which ones we can split up. So we know we're going to be using the quotient property. Okay, it's just important to realize we can't split this x plus 4, right? That has to stay. X cubed is going to turn into 2 natural log of 2 to the x. We can make a pretty good assumption at what we're going to be at, but it's easier if you just work through it. So log base 2 of x squared over the cube root x plus 4. First step, use the quotient property to split these up. So that's log of base 2 of x squared minus log base 2 of the cube root of x plus 4. The next thing we want to do is we want to use our properties of rational exponents to get rid of the radical, right? Since it's the cube root, that's really the quantity of x plus 4 to the 1/3 power. So once we do that, we're going to be left with log base 2 of x squared minus log base 2 of x plus 4 to the 1/3 power. Then final step is we use our power property of logarithms to bring the exponents out front. So that's 2 log base 2 of x minus log 1/3 log base 2 of x plus 4. Remember, expanding is just bringing it very, very wide, right? And condensing it is sucking it back together. All right, Now we're working opposite. We got to condense it. There's two variables. So if I'm just looking through this, I have two logarithms that are going to be multiplied by each other by the product property, and they're going to be divided by this quantity. Right? I can make a pretty good assumption of this on my head. In my head, 1/2, this 1/2 corresponds to the exponent, which means my square root is in the bottom. So my answer is between B and C already. Natural log of y has got to be up top. Should be pretty simple. But we're left with, yeah, that's going to be a nightmare. I just like the way this pen writes. All right, this will be the last one. So we have the 4 natural log of 2x plus the natural log of y minus 1/2 natural log of x plus 1. First thing I'm going to do, I'm going to bring my exponents back in using the power property. So this is the natural log of 2x to the 4th power. We'll simplify that plus natural log of y minus the natural log of x plus 1 to the 1/2 power. Okay, now I'm going to solve my my exponents. This one's going to turn back into a square root because I'm to the power of 1/2. This one I can take 2 to the 4th and just leave the variable. 2 to the 4th is 16. So I'm going to be left with natural log of 16x to the 4th plus the natural log of y minus the natural log of the square root of x plus 1. Now I'm going to reverse my product property and my quotient property. So these two are multiplied together and going to be on top. This one will be in the denominator. So my final answer, natural log of 16x to the 4th y, because those are all multiplied together, divided by the square root of x plus 1. So it looks like my answer choice is C. Okay, the last one says to estimate. We can actually run this through. You can think about it logically and get very close to the answer. If not, get the exact answer. Or we could use the change of base format and just round if we wanted to. It's really to pick your poison, but if you're going to think about it logically, remember logarithms, you're asking for the exponent. So what it's asking you is which exponent could we raise 3 to that would get you 7? Well, we know 3 to the 0 is 1, so that's not even close, right? 3 to the 1st power is going to be 3, so still not very close. 3 to the 2nd power is 9, and then 3 to the 3rd power is 27. So using that, which is closest to 7? Well, it'll be C, number 2, or C, 2, because 3 squared is 9. Or like I said, you could plug this into a calculator and take the log of 7 divided by the log of 3, and you'd get about 1.77. Rounded up would give you C as well. So since they estimated, it's just easier to think about it and think logically. All right, so we applied inverse properties of exponents and logarithms to simplify expressions. That was section 3.2. And a couple of the properties that I want to write up, just so you're aware of them again. They are your inverse properties, which state that log base B of b to the x is equal to x. This is the first one. And then b to the power of log base b to the x is equal to x. Make sure I wrote those up right. Okay, and the reason I want to use these inverse properties, because they're inverses, right? They make it easier. These are really going to come into play on how we solve this, okay, especially later on. So make note of these, make sure you understand them and how they apply. They make your life a lot easier, especially when it comes to simplifying. But we just want to make sure we have those down. So I'll give you a second to write them, and then we will continue. That should be enough time. I'm gonna get a workout in just erasing today. It's gonna feel awesome. Okay, and what are we doing today? And this one will carry into next week. We're going to apply the one-to-one property of exponential functions to solve equations. Then we're going to apply one-to-one property of logarithmic functions to solve equations. More or less, the one-to-one property is, here's an example of it right here. Okay, one-to-one property of exponential functions. So for any base b that is greater than 0 and b cannot equal 1, b to the x equals b to the y if and only if x equals y. Okay, so if we're looking at this, the examples, if 3 to the x is equal to 3 to the 5th, then x must equal 5. Right? This one is a whole lot easier to rationalize, because the only way you're going to get the same answer on both sides is if x is equivalent to 5, right? If it's 6, you have one more multiplication of 3 that's going on. If it's 4, you have one less. So it's got to be exact there. Okay, and then here is the part that's called exponentation. Okay, it says if the log of x is equal to 3, then 10 to the power of log of x is equivalent to 10 to the third. Okay, and that kind of, it doesn't really, it looks a little funky, but what you got to understand is it's a property of equality. Whatever we're doing on one side, as long as we do it on the other side, we're going to get the same answer, right? So if we were to just say, let's say we have the variable x, and that's equivalent to 4. Exponentation is adding a base and using these as the exponents, right? We do this so that we can use our properties, our inverse properties, to be able to solve them, okay? Because you end up with your inverse property where it's the same, the base to the power of a logarithm, that removes the logarithm, then you're just going to be left with a variable. So if we have x to the 4th, if I were to raise these to the power, or say exponent to 6 to the x is equivalent to 6 to the 4th, that doesn't materially change my equation, right? All I did is added a base. I'm treating these now as the exponents, and it stays the same because I've done whatever I've done on the left side of my equal sign, I've done on the right side. So the powers of equality, they still apply in this case. These two are still equivalent. If we wanted to figure out what 6 to the 4th was, I think it's like up in the thousands. But we could actually add another base. We do this so that our properties of logarithms will apply and allow us to solve these equations for variables. Okay, but it's a one-to-one property, and then it works backwards also, right? So if we're given this equation, 6 to the x is equal to 6 to the 4th, and they're asking us to solve for x, well, x has to equal 4, right? That's the only way that these two can be the same answer or to be equal. So we're going to add bases. We're going to take bases away. It's called exponentation. Okay, but it's a key thing in being able to solve these problems. So just trying to set it up before we really use it. I'll put the key concept back up. That way, if you need to write it down, I highly recommend it. So we can use it because we're going to use this one a lot today. Just a couple more seconds. It's so hard to judge how long you guys need to write it down. Because some kids will write down the words, some will just write the examples. So do I give you 2 minutes? Do I give you 1 minute? Do I give you 30 seconds? One of the toughest things as a teacher. But you always err on the side of caution. Give more time rather than less time. All righty, let's use this bad boy. Okay, so solve exponential equations using a one-to-one property. So we have solve 4 to the power of x plus 2, which is equivalent to 16x minus 3. So one thing that you had to pay attention to on your one-to-one property is it only works if you have the same base, right? 3 and 3. So we're going to have to manipulate this 16 to get it in the base of 4. Well, what's 16, or how does 4 relate to 16? 4 squared is 16. So I'm going to end up replacing this 16 with 4 squared. Okay, and then my one-to-one property kicks in, and then it turns into a pretty simple problem. So it's 4 to the x plus 2. It's equivalent to 16 to the x minus 3. As I just said, I'm going to change this to get it into the base of 4. 16 is 4 squared. So once I replace that, I'm left with 4 to the x plus 2 is equal to 4 squared to the x minus 3. And then, if you remember, there's a power called power to the power, which says if we have an exponent or base that's already raised to an exponent to another exponent, these two exponents are multiplied together. So after I multiply these, I'm going to be left with 4 to the x plus 2, which is equivalent to 4 to the 2x minus 6, because multiplying it through. Now, here's my one-to-one property. They have the same base, right? They both have 4 and they're both raised to the exponents. In order for this to be true and these to be equal, x plus 2 must be equal to 2x minus 6. So I can drop the base of 4. I'm just really dealing with the exponents now. I'll be left with x plus 2 is equal to 2x minus 6. And then I just solve for x. So isolate my variables. I'm going to bring this x from this side, bring it here. I'm going to add 6 on both sides so that these cancel out. Like that, and I'm going to be left with 8 is equal to x after I isolate. Because I subtracted this x from this side, so 2x minus x gives me x. Add 6 on both sides. 2 plus 6 is equal to 8. Okay, so you can see it looks like an intimidating problem right at the very beginning because the variable is in the exponent. But in all reality, using our properties and being able to use exponentation, the one-to-one property, it just kind of washes away, right? So we're left with our variable has to be equal to x, or it has to be equal to 8 in order for these two to end up equal. So we have the original equation. 4 squared is equal to 16, and since they're equal, we can substitute in. Then power of a power multiplies this exponent times x minus 3. Then your one-to-one property of exponents removes the base. Left with x plus 2 is equal to 2x minus 6. Solve for x. And we're left with x is equal to 8. So those ones are pretty simple. I mean, it looks intimidating, but if you apply your properties correctly, they really solve themselves. All right, here we have another good one. Okay, this one looks intimidating again because we're dealing with fractions, and everybody knows we don't like fractions. But at the end of the day, it's going to turn in to be pretty simple. The key is that we have to get the same base. Right? So do I really want to mess with 1/3? No, not necessarily. I'm going to be manipulating 1/81st right here. How does this relate to 1/3? Well, 3 squared is 9. 3 cubed is 27. 3 to the 4th is 81. So in all reality, 1/81st is 1/3 to the power of 4. Right? So I'm going to end up plugging that in. So I have 1/3 to the n is equal to 1/81st to the 2/3 power. Like I said, 1/81st is equivalent to 1/3 to the 4th power. So once I substitute that in, because they're equal, 1/3 to the 4th to the 2/3. Okay, then power of a power kicks on again. Where I multiply these two, I'm be left with 1/3 to the n is equal to 1/3 to the 8/3. And then my one-to-one property of exponents kicks in because I have the same base, the raised to an exponent, and the only way that these two could still be equal is if n is equivalent to the exponent I have on this side. So it allows us to drop our base. And once we do that, we're left with n is equal to the 8/3. All right, and that's the only way that these two can end up as equal quantities. We have the original equation. We substitute in power of a power to multiply our two exponents. The one-to-one property reduces it down and allows us to remove our base. And we get our answer as 8/3. And what you really got to understand is we're not materially altering any of these. We're substituting in equal quantities. And as long as we do it on both sides, it allows us to remove portions of the problem to simplify it, to make it an easier problem for us to handle. So that's your one-to-one property, or we have one more. So solve 25 to the power of x plus 2, which is equal to 5 to the power of 4x. So once again, I got to get the same base. So 25 is 5 squared. And then I'm going to use power of a power. And then I'm going to use the one-to-one property. And then it turns into a simple problem. So 25 to the x plus 2 is equal to 5 to the 4x. Make sure that's right. Substitution property of equality allows me to change 25 into 5 squared to the power of x plus 2, 5 to the 4x. Power of a power multiplies those. So that's 5 to the 2x plus 4. So you got to multiply. It's equal to 5 to the 4x. Then one-to-one property of exponents, because we have the same base. So it allows us to drop the base. So we're left with 2x plus 4 is equal to 4x. Okay. If I subtract 2x from both sides, I'm left with 4 is equal to 2x. Divide by 2 on both sides. I'm left with x is equal to 2. Just like so. I have to clean my board before algebra 2. It's going to be a nightmare. All right. Okay. So we're going to solve logarithmic equations using the one-to-one property of exponents. Okay. So here is where we get options. Now, options aren't a terrible thing. All it means is that there's multiple ways to solve these problems. Okay. One of the options that we have is we can switch them back into exponential format. So if you remember at the very beginning when we first started doing logarithms, it was log base b to the y is equal to x, right? So because it's an inverse, this, if we're going to change it to exponential format, is b to the x is equal to y. Okay, and they're flippable. This is writing it into exponential format. Sometimes this is beneficial because it allows you to really isolate the variables and be able to solve it pretty easy. Like if we have the base of 2 and x is 3, and we're trying to figure out what y is, well, what's 2 to the third power? 2 to the third power is 8. So being able to switch it into this format makes it a whole lot easier sometimes. But then we're also going to use exponentation as the other method, which corresponds to your inverse property of logarithms. Okay, but this is key. This is like the fundamental basis of logarithms. So you have to understand that in order to make it work. Or we can use inverse properties of logarithms to be able to solve. So our problem is 2 times the natural log of x is equal to 18. And we're working to solve for x. We want to find our variable. So we want to isolate it. First step, I can divide by 2 on both sides, right? Because it's 2 times the natural log of x. What that gives me is the natural log of x is equal to 9. Okay. Here is where I get my options. I had to do this portion. First option, switch it into exponential format. Okay, remember natural log always has a base of e. So what this means, if I switch it into exponential format, it says e to the 9th is equal to x. Okay, can I solve e to the 9th? Yes, I can. I can plug it straight into a calculator. Don't have to do anything else. That's just switching it into the exponential format. Plug that into a calculator. I'll get my value of x. I'll do that in a second. The other option is to use exponentation. Okay, and what exponentation does is I'm going to raise both of these, and they're going to turn into my exponents. And I want to be very, very strategic. I wouldn't want to use like 6, because 6 doesn't help me there. I want to use the base of e so that my inverse property of logarithms will kick in. So the second option is to exponentiate, and I'm going to change it into e to the natural log of x is equivalent to e to the 9th. Okay, what this does is allows the inverse property of exponents, which says that base b to the natural or to the log of base b to the x is equivalent to x. That eliminates this, where I'm just left with x on one side, and then I'm still left with e to the 9th. Okay, and that the property is that first one that I wrote up, or the second one is that b to the log base b of x is equal to x. That's the inverse property I used. In both situations, I end up with e to the 9th. Yep. as my answer. I can plug that into my calculator very simply, and I get 8,103. Point, want me to round it to the nearest hundredth, 0.08. So you can see options are good. They complicate stuff, but you just got to think which option's best for me. In this case, the easiest way is to solve it here, right? Just switching it back into exponential format. This one's a little bit longer process, but it's beneficial to understand it because not every problem is going to be able to come out this clean cut, right? It just doesn't work that way. Honestly, you should use the exponential format as long as you get the answer, like the log base, because the natural log of x is equal to 9. If these were switched, then it's in my best interest to do it this way. Because then I can remove all of that and I'll be just left. Because it doesn't have to be a variable here for my inverse property to kick in. So we get options. Both are pretty simple to solve. It's just a matter of applying them and using them properly. Okay, so we're using exponentation first. It's where we add the base. So we divide both times. We're going to divide each side by 2. Here's the exponentiate. So e to the natural log of x. Then the inverse property kicks in, where x is equal to e to the 9th. We get 8103.08. And then the second one, which is the easier in this problem, we still divide by 2 on each side. Then we switch it into exponential form. So x is equal to e to the 9th, because our base of natural log is always e. Plug it into a calculator, we get the same answer. So you can see it's just what fits our situation best. Okay. So this one is a little bit tougher. Okay. So we're solving 7 minus 3 log of 10x, which is equal to 13. In both cases, I think I'm just going to exponentiate this one. Should be pretty simple. So 7 minus 3 log times log of 10x is equal to 13. So first step, I just start to isolate, right? I want to get the log by itself, so I'm going to minus 7 on both sides. It's going to give me 3 times the log of 10x is equal to 6. I'm going to divide by 3 on both sides. I'm left with the log of 10x is equal to 2. Okay, so in this case, remember I have the base of 10. It really doesn't really help me much. Okay, so I'm going to exponentiate. I have 10 log 10 to the power log of 10x is equal to 10 second. Negative. Yep. Okay. By doing that, says that I can remove the logarithm. So I'm just left with 10x is equal to 10 squared. Divide by 10 on both sides. And x is equal to 10. Right there. I think I did that properly. We shall see. Oh, crap, I didn't show it. Oh, thank you, Mohammed. I did make a mistake. Or Rosalind, sorry. I divided by 3 on accident. So I did make a mistake here. I should have divided by a -3 to get a -2. So that's there. Thank you for correcting me there. Divide by negative. Come on, Mr. Burns, you're better than that. You're better than that, not by much. But then the same thing ends up kicking off. Power to power drops because I exponentiated. My inverse property here leaves me with 10x is equal to 10 to the negative second. And then when I divide by 10 again, I'm left with that x is equal to 10 to the negative third. Thank you for that, Rosalind. Completely materially altered. But that should be our final answer. But you can see this one, I couldn't really write it into exponential format. Right? I would have been 10 to the negative second is equal to 10x, and then I would have divided there. So I could have, but it's just a little easier to use my inverse property. See how they solved it. So there's our original equation. They minus 7 from both sides. Divide by negative 3. That's where I did it wrong because I divided by 3 and not negative 3. Oh. They chose to write it in an exponential format. That's fine. Either way, you're going to get the correct answer. And then once you divide by 10 on both sides, you get 10 to the negative third. Or 1/1000th. You can write it into a fraction. I would have just left it 10 to the negative third. But that's okay. Here, we got to use the power property. Okay, this log base 5 of x to the fourth. We're going to bring that 4 out front, and then we're going to divide. It should make it pretty simple for us. All right, so we have log base 5 x to the fourth equal to 20. Okay, first thing that I want to do is I want to use my power property of logarithms to bring this exponent out front. So that's going to be 4 log base 5 of x is equal to 20. I'm going to divide by 4 on both sides. I get log base 5 of x is equal to 5. Here in this case, it's a little easier to change it into exponential format, which says that 5 to the 5th is equal to x. 5 to the 5th is equal to 3,125. Although they're saying round to the nearest hundredth. Yeah. Sorry, I clicked through it. Brings you the original equation. They use the power property to isolate the exponent. Then they divide. Then they write in exponential format to get your answer of 3,125. You could exponentiate this again. Put this at this point right here. Put them both to the base of 5. And if every time you exponentiate, you want to use the base that the logarithm is. So if this was just common log, I'd use the base of 10. If it was natural log, I'd use the base of e. So in this case, to match up, I would put it to 5 to the power of the log base 5 of x. Inverse property gives you x. And then you're still left with x is equal to 5 to the 5th. So the stuff, you know. Okay. This one's a little bit, it's a little bit tougher. It's not too terrible though, but we're solving the log of 2 to x. Log base 2 of x cubed is equal to 18. And we're solving for x. So I'm going to use the power property, which would give me 6 out front here. And then I'm going to divide by 6 to get log base 2 of x is equal to 3. 2 to the third power is equal to 8. So x, it has to be equal to 8. Yes. But power property, to bring this exponent out front, those two get multiplied together to get 6. Then I divide by 6. And then it's pretty simple once you switch it into exponential format. Like I said, you got options. You just want to be strategic on how you use them. Okay, here will be the last key concept for today. I am going to extend this lecture into next week because this stuff is quite a bit. So we're just going to scratch the surface today, give you some homework problems, and then we'll be off and running. And I'll finish up this section next Monday where we get into a little bit more complex problems. But this will be a good starter. So one-to-one property of logarithmic functions. Okay, it's very similar to the one-to-one property of exponential functions. So for any b that's greater than 0 and b cannot equal 1, log base b of x is equal to log base b of y if and only if x equals y. So in this case, you can see here, if I have the log base 2 of x is equivalent to log base 2 of 6, then x and 6 must be equal. Right? One-to-one property allows me to remove it. The same way that we exponentiate, we can take the logarithm or the natural log or the common log of both sides. Okay? Because they have to be the same. And it's equality. So as long as what we're doing on the left matches what we're doing on the right, we have no issues. That's your second example. So why would this benefit you? Well, one, because then you're just left with, you'd be just left with a variable according to your inverse property. Log base b of b to the x is equal to x. So like in this case, if e to the y is equal to 2, then the natural log of e to the y is equivalent to the natural log of 2. Why does this help us? Well, right here would be your inverse property. It's a natural log, so it has the base e of e to the y. That has to be equal to y. And then y would be equal to the natural log of 2. So like I said, you want to use these inverse properties to help yourself because you can remove logarithms that way. But the key is you got whatever you do on the left, you have to do on the right. Okay, so solving exponential equations using the one-to-one property. So if I'm looking at this here, I have the log base 2 of 5 is equal to the log base 2 of 10 minus log base 2 of x minus 4. So this side, this right side here, what does that look like? Well, it looks like a quotient property. So I can rewrite this as one logarithm with 10 divided by the quantity of x minus 4. Then my one-to-one property is going to kick in and I can just solve for x. Okay, it looks intimidating, but if I use my properties and being able to expand and condense these properly, it's a pretty simple question. So log base 2 of 5 is equal to log 2 of 10 minus log base 2 x minus 4. So first step, like I said, I'm going to condense these down. When I do that, I'm left with log base 2 of 5 is equal to the log base 2 of 10 divided by x minus 4. Okay, here's where my one-to-one property kicks in. That's a terrible 5. Here's where my one-to-one property kick in. They both have the same base. There's both the same logarithms. It allows me to drop it because 5 must be equivalent to 10 divided by x minus 4. So one-to-one property of logarithms gives me this. Okay, now I solve for x. So I multiply both sides by x minus 4. On this side, I'm 5x minus 20 after the multiplication is equal to 10, plus 20 on both sides. Gives me 5x is equal to 30. Divide by 5 on both sides. Gives me x is equal to 6. So I condense it. 1-to-1 property of logarithms allows me to drop the logarithms. Then multiply both sides by x minus 4. Add 20 on both sides, divide by 5, get x is equal to 6. Okay, and then we always want to check this. Okay, and what I mean by check it is if x is equal to 6, I'm going to plug that in. Now, why would I do that? Because remember, I cannot have a negative as the answer when it comes to a logarithm. Okay, I'm not saying the answer on the outside. I'm just saying whatever I write it, log base b of x, this x cannot be negative at any point. Okay, so when I plug 6 in, I get 6 minus 4 is 2. That works, right? As long as it's not negative. Okay, if I were to come up with an answer of 3, 3 minus 4 gives me a negative 1. That is, you can't do that. Original equation, condense it using quotient property, the 1-to-1 property of logarithms. Multiply each side by x minus 4. I made a typo and put 4.5. Add 20 to isolate the variable. Divide by 5 to finish isolating the variable. And you get that x is equal to 6. I think I only have like 2 more examples to go over, but it should be pretty quick. Okay, this one turns into a question where we're going to end up factoring. So if we're just analyzing right now, I can't do anything with this x squared plus x because that's one whole quantity, right? Like thinking on how we would expand or condense. It's already condensed and it's already in a format where the 1-to-1 property works here, right? The 1-to-1 property, I can drop these now and be left with x squared plus x is equal to 20. Okay, but that doesn't really help me. Or it does help me because it isolates and gets rid of the logarithms. And then I'm going to end up having to factor and solve it like a quadratic. If you guys remember from the first semester, when we solved for quadratics. All right, so I have log base 5 of x squared plus x is equal to the log base 5 of 20. Okay, so like I said, it's already in a format where the 1-to-1 property kicks in. So I don't have to alter these at all. So I can just really rewrite them, dropping the logarithms. So x squared plus x is equal to 20. Then I'm going to subtract 20 on both sides, because that gives me the x squared plus x minus 20 is equal to 0. This point, if you really wanted to, if you didn't want to factor it, you could actually graph that and see where they cross the x-axis, because they'll be the roots, the same way that we did way back in August. Easier way is to just factor it. I'm looking for 2 terms that multiply to be a negative 20 that add up to be a positive 1. Those 2 terms are x plus 5 and x minus 4. Okay, what does that do for me? If I set them both equal to 0 and use the zero product theory, I'm going to get that x is equal to -5 and x is equal to 4. Set them both equal to 0 and then solve for x. This one, x plus 5 is set equal to 0, subtract 5. That's how you get x is equal to a -5. Then x is equal to 4. Same reason. Okay, through the zero product property. And then at this point, like I said, I'd always want to plug them back in because there's these things called extraneous solutions. Right? I cannot end up with a negative here. So -5 squared is 25 plus a -5 is 20. Log base 5 20. Right there if I were to plug -5 in. If I were to plug 4 in, 4 squared is 16 plus 4 gives me 20. Both of those would work because that does not turn into be a negative. So 1-to-1 property, they subtract 20 from each side, then they factor it. So x minus 4, x plus 5, then the zero product theory, zero product property kicks in. So I have to set both of these equal to 0 and solve for x. So I get -5 or 4. Check the solution by plugging it in. -5 squared is 25 plus a -5 is 20. That checks out. 4 squared, 16 plus 4 is 20. So we're good on both of those. All right, I believe this is the last one. This one is actually a little bit harder problem because I have to manipulate it to get it into the format where my properties of logarithms will kick in. So you can see how it's log base 3 of x plus log base 3 of x minus 2. So I'm going to use the power property or the product property, the product property of logarithms. And then my 1-to-1 property can kick in. So log base 3 of 15 is equal to log base 3 of x plus x minus 2. Okay, so like I said, first step, reverse the product property to condense these down. So that's log base 3 of 15 is equal to the log base 3 of x times x minus 2. Okay, then I distribute. Get log base 3 of 15 is equal to log base 3 of x squared minus 2x. Now my 1-to-1 property of logarithms will kick in, allowing me to drop the logs. So I'm going to be left with 15 is equal to x squared minus 2x. Okay, subtract 15 on both sides. To get 0 is equal to x squared minus 2x minus 15. Factor two terms that add up to be, or that multiply to be a -15, add up to be a -2. That is x minus 5, x plus 3. Set those equal to 0 and solve. Get that x is equal to 5 and a -3. Okay, here's the kicker. We have to check them. So if I plug 5 in, log base 3 of 5 plus log base 3 of 5 minus 2, which is 3. So 5 is good. Okay, -3. Log base 3 of -3 can't happen. So even though I ended up with 2 solutions, -3 is what's known as the extraneous solution. Because you cannot have a negative right here. So log base 3 of -3, that doesn't work. Log base 3 of -5, that doesn't work either. So our final answer is going to be A. All right. So that's what I have for you. Okay, that's your lecture today. We'll pick up next week.